Good morning. Let me share the screen. Okay, for some reason the connection went down, but now you should be able to see the screen with the usual set of figures showing the typical problems. You should be able to see the typical problems that are solvable in quantum mechanics with an analytical approach. Today we shall see another example in which the form of the potential energy is not piecewise constant. This example is extremely important because there are many applications of it. And the example is called the case of the harmonic oscillator. Today we are still in the part of the lessons that are provided as exercise. When we get the lessons in which the material is supposed to be part of the exam, I will tell you. Okay, for today we are still in the part that is related to the exercises. So let me go to the page of the linear harmonic oscillator. Let me rotate screen. Okay, we are here. And we examine first the linear harmonic oscillator in the classical case. It is a very easy problem in classical mechanics. We consider a one-dimensional situation in which we have a particle of mass m that is able to move along the x-axis. And we assume that the force, you can see it in the second line of the page, the force is proportional to x with a negative factor, okay? So the force can be written as minus c. C is a positive constant that is called the elastic constant, times x. We already met a situation like this that actually was much more complicated, because when we considered, as you remember, the set of atoms bound together, And we assume that the atoms were tightly bound. So we could assume that the displacements with the equilibrium positions are, as you remember, we use the simplified expression of the potential energy that was the expansion in the Taylor series of the potential energy around the equilibrium positions. And then we truncated the series to the second order. So we had a potential energy that was quadratic and the force that was linear with respect to the displacements. This is exactly the same case that we are discussing here. Simply here we are considering a single particle. Then, if we have a force that is proportional to the displacement with respect to the origin in this case, okay, then the potential energy, of course, is quadratic, is written in the third line. It is V equal to Cx squared divided by 2. And this is the typical example, for instance, of a mass that is connected to the origin with the linear spring. So when the particle is displaced to the right of the origin, the force pulls the particle to the left, back to the origin, because x is positive, and when the particle is on the left of the origin, the force is positive and pulls the particle again towards the origin. So, in conclusion, the particle keep oscillating from left to right. The total energy is, of course, a constant because we have a potential energy. So the total energy is, as you see in the formula, P squared over 2m plus 1/2 Cx squared equal to the total energy, that is a constant, and the equation is solved and provides an oscillatory motion which xm is maximum elongation, and omega is the angular frequency of the oscillation and is given by the square root of the elastic constant over the mass. Now we have to find the quantum equation corresponding to this. So we have to go from the classical situation to the Schrödinger equation independent of time. But before we do that, we should appreciate the importance of the problem, because we already met one case. That was the case of the system of atoms bound together that looks extremely complicated. But when we expand the potential energy of the system and truncate it to the second order, we find a problem that is eventually separable. Because, as you remember, when we introduce the normal coordinates or the normal modes of oscillation, we split the problem of many particles interacting with each other into a problem in which each degree of freedom is independent from the others. And the equation of the individual degree of freedom is exactly the equation of the linear harmonic oscillator. So as you remember, a crystal can be approximated as a superposition of linear oscillations. Another very important problem that is formally completely different, but or physically different, but that can be reduced to a set of equations that again are the equations of linear harmonic oscillators, is that of the electromagnetic field in vacuum. We did not perform this calculation, but I just give you the results. If you take a region of space with no charges, in which we have the presence of the electromagnetic field, and we start from the Maxwell equations and we manipulate the Maxwell equations, after some lengthy calculations, we can reduce them to a set of equations that describe the so-called oscillation of the electromagnetic field. So the electromagnetic field in vacuum, as you know very well, can be described as the superposition of linear modes of oscillations. And each mode of oscillation of the electromagnetic field again has the form of the equation of the linear harmonic oscillator. Can be reduced to the equation that you can see in the first line of this page. So why is this important? It is important because if we succeed in calculating the solution of the Schrödinger equation for this single problem, for the linear harmonic oscillator by itself, then we can apply the solution to many important problems. For instance, we can quantize the motion of the atoms of a crystal. We can treat the motion of the atoms in a crystal using quantum mechanics by simply replicating the outcome of the calculation that we are now going to start. And the same thing applies for the electromagnetic field. So the quantization of the electromagnetic field becomes possible right after we solve the problem that we are facing today. You may anticipate that the quantization of the electromagnetic field leads to the concept of photon. We know what the photon is because we introduced that starting from the experiments and from the interpretation of the photoelectric experiment, okay? We did not do any calculations, okay, but we introduced the concept of photons. And we expected that the outcome is possible when we consider a crystal. Because if a crystal can be described, if the motion of the atoms of a crystal can be described as a superposition of linear harmonic oscillations like the electromagnetic field, then we can quantize the crystal in the same way as we do for the electromagnetic field. In fact, the modes of oscillation of the crystal after the quantization has been completed is described in a very similar way as for the electromagnetic field. And we introduce in a crystal the concept of phonon, that is a particle, a fictitious particle, that is the correspondent of the photon in the electromagnetic field. Photons have energy and momentum and are the particles that describe the oscillation modes of the electromagnetic, of the crystal. So now we start the calculation, and the first thing to do is that we must transform the expression of the total energy of the classical case in the linear harmonic oscillation into the quantum operator, and we use the same recipe that we have used in the other cases. We replace the momentum P with the momentum operator, that is minus j h bar derivative with respect to x. And so we obtain the Schrödinger equation that you can see below. The Schrödinger equation is minus h bar squared over 2m, the second derivative of the space part w of the wave function. And then, for convenience, when we consider the potential energy, instead of keeping the symbol of the elastic constant, C, we replace it. You see the definition of the angular frequency is the square root of C over m. So we extract C as m multiplying the square of the angular frequency, and we replace it in the equation. So the potential energy is written 1/2 m omega squared x squared times w. Okay. We can notice immediately the property that the angular frequency is fully determined by the parameters of the classical case, that is the elastic constant and the mass of the particle. We already observed this property in the analysis of the crystal. You remember that in that case we had many values of omega squared that eventually were the eigenvalues of the equation that we were solving. Okay. So now we have to solve an equation like this, that is a differential equation of the second order in which the potential energy is not a constant, it is quadratic with respect to position. Before we start the solution of the equation, it is convenient to eliminate the constant. So we simply renormalize the equation by dividing all terms by h bar omega. So on the right-hand side, the total energy E is divided by h bar omega. Of course, h bar omega has the units of an energy, so the ratio that is defined here is called epsilon, is a quantity with which is a pure number. And then we also define a normalized abscissa. Instead of x, we introduce a new abscissa that we call psi, that is equal to x times a constant parameter that is the square root of m omega divided by h bar. If so, we eliminate all constants and obtain an equation that is dimensionless. And the equation is written on the bottom line. It is h prime operating on w equal to the eigenvalue epsilon times w. And the new Hamiltonian h prime is 1/2 that multiplies the square of psi minus the second derivative with respect to psi. So this is just a normalized Hamiltonian. We have a simpler, an equation that looks simpler because there are no parameters anymore. Now, there are two possible methods for solving this equation. One method is by brute force. That is, what we do is we expand the solution W formally in a power series. So we expand it in a series in which the powers of psi appear. So we have a zero order term, a first order term, and so on and so on. And this is, of course, is an infinite series. Then we replace the series in the equation. You can immediately understand that the right-hand side, epsilon times W, contains the series as is, because W is expanded into the series. That the terms that are multiplied, of the terms of the series that are multiplied by psi squared have the same terms of the series in which the power is increased by 2, because we multiply a series by x squared, okay? And the other term, the derivative with respect to psi 2 times, has the same terms in which the powers are decreased by 2. Consider, for instance, the sixth term of the series is a term in which we have psi to the sixth power. If you take the second derivative, you have psi to the fourth power, okay? So we have a mixture of terms, and the solution by series is simply consists in imposing that the coefficients of the series are such that the left-hand side of the equation becomes equal to the right-hand side. So we find the relation among the coefficients, okay? After we complete this job, we find all the coefficients of the series, and we have the unpleasant outcome that the series diverges. Okay, so the series cannot be accepted as is because we cannot accept solutions that diverge, as you remember, because they do not have any physical meaning. So in order to, since the procedure by series is legitimate, but on the other hand, we find that the series diverges, the only possible solution is to truncate the series, so to impose that the series becomes a polynomial. And when we do so, we find eventually the solution. Okay, this is a possible way for solving the equation, but it is not very elegant. It is by brute force. Another possible way that is much more elegant stems from the observation that if you look at the Hamiltonian, you see that the Hamiltonian qualitatively, only qualitatively, it is made of the difference of psi squared, that is the coordinate to the second power, minus the second derivative, that is a derivative to the second power. So qualitatively, it is like the difference of two squares, okay? And you know that the difference of two squares can be factorized. If the derivative d2 over this I squared is replaced for a second with the number a squared, we have psi squared minus a squared that can be written as psi minus a times psi plus a. So we can factorize the problem. Factorizing an operator is not as easy as factorizing a number, okay? But we can proceed on this line. So we shall attempt to factorize the Hamiltonian. Why is it useful to factorize the Hamiltonian? The reason is that if you factorize an operator that is of the second order, you eventually succeed in reducing the operator to the product of two first-order operators. And then you can deal with one of these operators at a time. And of course, having first-order operators is equivalent to solving first-order differential equations. And these are much easier than the second-order equation. So we shall proceed by attempting to factorize the operator. And for this, we start introducing an auxiliary operator that we call a hat, as you see in the middle of the line. And this operator is defined as 1 over the square root of 2 times psi plus derivative with respect to psi. So it is a first-order operator. Then we can make a calculation by which essentially we extract from this operator, we extract the adjoint operator of a hat. You remember that the adjoint operator is the operator that, in quotes, stays on the left in the scalar product and provides the same result as when using the original operator in the same scalar product. So for this, we take any two functions, f and g, that vanish at infinity, so they fulfill the normalization condition. And we calculate the integral from minus infinity to plus infinity of g star, followed by a applied onto f. Then we replace a, so we have 1 over square root of 2, and then in the integral we have the term with psi that is unchanged, and then we calculate the other term by parts. Okay, so you see in the line, in the first line of the calculation, there is already the integration by part. The term with the derivative is replaced with f minus f with the derivative applied onto g star. So it is just an integration by part, okay? But you see immediately that since g and f vanish at infinity, the term in brackets, g star f limited by at minus infinity and plus infinity is equal to 0. So we are left with the integral of another operator, that is the operator that is similar to a but with the minus sign instead of the plus sign. And this operator is called a dagger. So by this calculation, you see that if we start with a applied onto f, we end up with a dagger applied onto G. So A dagger is, as you remember, the adjoint of A. And the expression of A dagger is similar to that of A, but with the minus sign. Obviously, A dagger is different from A. So this operator A is not Hermitian. And then we can calculate the commutator of A and A dagger, and we see immediately that the two operators do not commute, because if you calculate A times A dagger minus A dagger followed by A, you don't find 0. If you found 0, they would commute, okay? You don't find 0, you find the identity, okay? Finally, if you instead calculate the other expression that you see on the same line, A followed by A dagger plus A dagger followed by A, you obtain 2 times the Hamiltonian prime. So this is important because, of course, the operation of factorization works differently than in the case of numbers, okay? But anyhow, we have obtained operators that are of the first order, because both A and A dagger contain only the first derivative, so they are first order operators. And you see that by suitable combinations of them, we can reconstruct the Hamiltonian. We can also manipulate a little bit these expressions, because we can introduce a third operator that we called capital N. This operator is defined as A dagger followed by A, and it is called the number operator. And if you combine the two expressions that are in the middle of the line and introduce the definition of the number operator, you find that the Hamiltonian prime applied to W is equal to the number operator applied to W plus the identity applied to W divided by 2. Simply because if you look at the line above, Hamiltonian prime is equal to 2 times the number operator plus the identity. Okay, and this is simply found by combining the two expressions involving A and A dagger. Why is this result important? This result is important because at the same time, the Hamiltonian prime applied on W is the left-hand side of the original eigenvalue equation. So it must be equal to the eigenvalue epsilon times W. Okay. So if you now observe that the identity applied on W is W itself, and you bring to the right-hand side the part of the expression that embeds the identity, you have that the number operator applied onto W is equal to epsilon minus 1/2 times W, and you can use a shorter symbol, epsilon minus 1/2. You call it Ni. Ni is some real number for the moment that multiplies W. So the conclusion is that this operator N, the number operator, has the same eigenfunctions W as the original Hamiltonian H prime, and its eigenvalues differ by the constant 1 1/2 with respect to the eigenvalues of the original Hamiltonian. So if we succeed in solving the equation for the number operator, then we shall obtain automatically all the eigenfunctions of the Hamiltonian and also all the eigenvalues of the Hamiltonian. Okay, and we shall see that solving the eigenvalue equation for the number operator is relatively easy. So now we proceed and we find some properties of the eigenvalues of the number operator. You may remember by looking at this definition that the number operator is defined as A dagger followed by A. So it is the product of two first-order operators. You remember that A is non-Hermitian, and also A dagger, of course, is non-Hermitian, but we shall find in a second that the product N is Hermitian. Well, it is obvious, actually, because you see N is like the Hamiltonian, and then we have the addition of the identity. So the Hamiltonian is Hermitian. The identity is also Hermitian, and the sum of Hermitian operators is Hermitian. But we can do more than that, because we can make a calculation from which we find also some properties of the eigenvalues. Okay, so N is Hermitian, so we know for sure that the eigenvalues Ni of the number operator are real, because Hermitian operators have real eigenvalues. And another property that must be calculated, we shall do it now, is that the eigenvalues of N are non-negative. So they are real positive numbers. We can do it, we can demonstrate this by multiplying on the left the eigenvalue equation for the number operator by W star, and then we integrate from minus infinity to plus infinity. So we have this expression here, and we have an integral in which we have W star, then it is followed by the number operator, that is A dagger A, operating on W. You remember that in an expression like this, we can take, for instance, A dagger, that is the operator on the left of A. We can think of A dagger as an operator operating on AW. Okay, AW is a function, so we have A dagger operating on AW. And then we can bring this operator on the left. You know that we can do it provided we replace A dagger with its own adjoint. But the adjoint of the A dagger is A. So if we bring A dagger on the left of W star, we have A W in parentheses star multiplying again AW, that is, as you can see on the right of it, the square modulus of AW, okay? Then the right-hand side of the eigenvalue equation is Ni times W, then we multiply it by W star and integrate, so we obtain the integral of the square modulus of W times Ni. Ni is a number, so we can bring it out of the integral. Now, the conclusion is that since W is an eigenvalue, is an eigenfunction of the equation, W is cannot be identically equal to 0, okay? So the square modulus is strictly positive. The integral is strictly positive, okay? So we have a relation in which the integral on the right is strictly positive. It is multiplied by a real number. And then we have an integral that is the integral of the square modulus of AW. So if AW is identically 0, then Ni will be equal to 0. If instead AW is not identically equal to 0, then the integral of AW squared is strictly positive, so that Ni is also strictly positive. So the conclusion is, if AW is non-zero, then Ni is strictly positive. If instead AW is 0, then Ni is 0, okay? So the conclusion is that Ni is equal to 0 if and only if AW is equal to 0. Otherwise, Ni is strictly positive. So far for the eigenvalue. Then we find another relation that is also important. You remember that in the previous page, we have obtained a relation involving the commutator of A and A dagger. The commutator is equal to the identity, okay? So what happens if we multiply this relation that is repeated here? We multiply this relation on the left by A dagger. When we do so, in the first term, we have A dagger followed by A, that is N. This is followed by A dagger, whereas on the left, we have A dagger followed by A dagger A, that is N. So we have, of course, the right-hand side is the identity times A, that is, A dagger, that is equal to A dagger. So we have a relation of the form N followed by A dagger minus A dagger followed by N equal to A dagger, okay? If we bring this part with the negative sign to the right, we have that N followed by A dagger is equal to A dagger followed by N plus identity, okay? Now the issue is, what happens if we consider this new operator, N followed by A dagger, and apply the operator onto any eigenfunction W of N? Let's try to do it, okay? Let's see what happens. We take N A dagger and apply it to W. Then we exploit the form of the right-hand side. So we have A dagger followed by N plus identity operating on W. We see immediately that N over W gives you the eigenvalue Ni times W. And of course, the identity over W is W. So we have A dagger W. Ni is a number, so we can extract Ni and bring it to the left, so that when we collect A dagger W, we have Ni plus 1 multiplying A dagger W. So now you can look at this equation. If you look at the extreme left, you have the operator N operating on function A dagger W. A dagger W is some function. It is the result of the application of A dagger onto W. So this operator n on this function is equal to n plus 1 times the same function. So this is again an eigenvalue equation in which the eigenfunction is a dagger w, and the eigenvalue is n plus 1. So we have found an interesting formula that shows that if w is an eigenfunction of the number operator n corresponding to the eigenvalue n, then a dagger w is also an eigenfunction of the same operator n corresponding to the eigenvalue n plus 1. So we have found another eigenfunction and another eigenvalue of the same operator. What we can do is, let's see what happens if we keep going. Okay, so instead of having n a dagger w, why don't we calculate n a dagger and a dagger again w? Okay, we can do it immediately because the procedure is exactly the same as above. And what we find is n plus 2 times a dagger w. So you see that given any eigenfunction w corresponding to the eigenvalue n, we can calculate automatically a full group. This group is called ladder, a full ladder of eigenfunctions and eigenvalues by simply starting from the original eigenfunction w and operating on it using a dagger. And for each a dagger that we put in front of w, we increase the eigenvalue by 1 unit. Okay, so we find from one eigenvalue, we find infinite eigenvalues and eigenfunctions simply by adding an a dagger times the value by 1. Okay, this is fun. And we can immediately ask if we can go up in the ladder by increasing one by one the eigenvalues. Can we also go backwards? Can we find another trick by which we go back and decrease the eigenvalues one by one? And the answer is in the positive. We can do this. Now it is 10, so we have to stop, but we shall see what happens when we decrease the eigenvalues one by one in 10 minutes. For the moment, we stop. Okay, so we continue our reasoning. We are back on the page in which we were doing the calculation of the ladder of the eigenvalues. And as I anticipated, we now want to check whether it is possible to find a procedure by which we go backwards in the calculation of the eigenvalues. And this is again done starting from the commutator of A and A dagger. And in this case, instead of multiplying on the left by A dagger, we multiply both sides on the right by A. So what we find is another expression that in this case reads A followed by N minus N followed by A equal to A. So now we bring A from right to left and NA from left to right. What we obtain is that A followed by N minus the identity is equal to N followed by A. Now again, we apply this operator onto any eigenfunction W of the number operator, and by a similar calculation we find that if W is the eigenfunction of N corresponding to the eigenvalue Ni, then A operating on W is also an eigenfunction of the number operator N corresponding to the eigenvalue Ni minus 1. So we have found now the possibility of going backwards along the ladder. So we have the possibility of going up, Ni plus 1, plus 2, etc., and the possibility of going down, Ni minus 1, minus 2, etc., etc. However, we have a problem now, because if we keep going backwards, Ni minus 1, Ni minus 2, etc., sooner or later, we go into the negative numbers. If we keep decreasing by minus 1, by 1, we'll eventually enter the negative numbers, okay? But earlier in the game, if you look at the first line on the page, we demonstrated that the eigenvalues of the number operator cannot be negative. So the demonstration that we use to demonstrate that Ni cannot be negative is perfectly legitimate. But also the procedure by which we go backwards into the ladder is also legitimate. So the first calculation shows that Ni cannot be negative, and the second calculation seems to show that Ni can be negative. So we are now in a contradiction. How do we get out of the contradiction? Well, we may observe that in all these analyses, the only information that we have is that the eigenvalues are real, okay? So we made all the reasoning assuming that the eigenvalues are just real numbers. But this brings to the contradiction. let's make another assumption that the eigenvalues are not just any real numbers, but they are integer numbers. Okay, so let's simply assume that ni is an integer. Okay, so when we proceed upwards in the ladder, nothing changes. We have ni plus 1, ni plus 2, they are all integers. When we go backwards in the ladder, starting from integer, at some point we hit exactly 0. Okay, we reach 0. But you remember, when we reach 0 from the formula on the first line, we realize that if ni is 0, ni is a legitimate eigenvalue, also if it is 0, okay? Then the left-hand side of this equation is 0, which implies that A operating on W is 0, identically 0, okay? But a function that is identically 0 cannot be an eigenfunction of an operator, okay? I mean, it is an eigenfunction of an operator, but it is the trivial solution, the solution that is of no interest, okay? So when we hit ni equal to 0, then in the equation that we have on the first line, the left-hand side is 0, AW is 0, so it is not an eigenfunction anymore. That means that we have to stop. We cannot proceed further, okay? Because we do not find an eigenfunction anymore. So if you look at the last line, okay, when you hit a 0, ni is equal to 0, you cannot go to -1 anymore, because the corresponding eigenfunction would be AW, and AW is not an eigenfunction anymore, okay? So by limiting the consideration of the eigenvalues to the integer numbers, 0 included, so 0 or positive integers, we eliminate the contradiction, because we find automatically the method for stopping the ladder in the backwards direction. Okay. This trick of imposing that the eigenvalue is an integer is the same thing that we would find by using the series expansion that I mentioned earlier, okay? If we find the series and we then understand that the series diverges, in order to prevent the series from diverging, we have to truncate the series, and this is done by imposing that the eigenvalues are integers. So we find again the same thing, okay? The eigenvalues must be integers. Conclusion. The only acceptable values of the eigenvalues are the integers, the non-negative integers. So instead of using the symbol ni, we use the symbol n. N is either 0, 1, 2, etc., etc., etc. Okay? So we have found, in a relatively simple way, we have found the eigenvalues. Okay? Now we must find the eigenfunctions, okay? But in order to find the eigenfunctions, we know that when we reach the eigenvalue equal to 0, n equal to 0, you remember, what we find is that AW is 0, okay? So we cannot say anymore that AW is an eigenfunction because it is equal to 0 and it is not acceptable. But W is an eigenfunction, okay? It is the eigenfunction that corresponds to the eigenvalue n equal to 0, okay? So we know that W in this formula, AW equal to 0, is an eigenfunction. Now we can write the expression AW equal to 0 explicitly. So instead of using the symbol W, we use the symbol W0 because W is the eigenfunction that corresponds to n equal to 0, okay? Then we replace A. As you remember, A is 1 over the square root of 2 times x plus derivative with respect to x. When we apply this on W0 and we equate this to 0, we have a first order differential equation that is easily solved. So essentially, the factorization has worked because we have found a first order equation whose solution is the eigenfunction W corresponding to n equal to 0. So at least we have found one eigenfunction. By the way, you can see immediately that the equation is separable. So we can write it as dW0 over W0 is equal to minus psi d psi, and this of course gives you a Gaussian, okay? Psi d psi is 1/2 d psi squared, okay? So we find a Gaussian. C0 is for the moment an undetermined constant, okay? And apart from this constant, this is the eigenfunction of order 0 of the number operator, but as you remember, it is also an eigenfunction of the Hamiltonian, okay? How do we find the constant C0? Simply by imposing the normalization. So we take the square of W, and then we integrate it over the real axis, and then we impose that this integral is equal to 1. The integral of a Gaussian is something that we are able to do. So eventually we find that the normalization constant C0 is equal to pi to the minus 1/4, okay? So we have found one eigenfunction, the eigenfunction corresponding to the minimum eigenvalue n equal to 0. How do we find the other eigenfunction? Very easily, because now we have to go up along the ladder. And you remember, to go up along the ladder, we simply increase the eigenvalues by 1, and we operate on W with a dagger. So if we take W0 and we operate on it with a dagger, we find W1, okay? Obviously, this is a mechanical calculation because W1 will be a dagger over W0, so it is just a multiplication by psi and a derivative with the minus with respect to psi, so practically immediate, okay? After finding W1, we find W2 corresponding to the eigenvalue n equal to 2, again by doing a dagger operating on W1, and so and so and so. For instance, W1 is 1 over the square root of 2, and then we apply psi over W0, and then we have minus derivative of W0, and by some manipulation we find that this is it. It is like having W0 multiplied by psi with some constants, okay? You see immediately that the initial eigenfunction is even with respect to psi because it is a Gaussian. The next one, W1, is found from the original one multiplied by psi, so it is odd because W is even but psi is odd, okay? So what we find is that the eigenfunctions of the linear harmonic oscillator are alternatively even or odd. Those of even index are also even. Those whose index is odd are also odd. Okay. Another issue is that for a given value of the eigenvalue, the eigenfunction is unique. To index 0, we have found one and only one eigenfunction W0. Then to index 1, we associate again one and only one eigenfunction, that is W1, and so on. So the eigenfunctions of the linear harmonic oscillator are non-degenerate. They are all the eigen values are, as you remember the name, they are simple. Okay. Now we have to go back to the non-normalized quantities. There is a demonstration that we skip in which it can be demonstrated that all the eigenfunctions of the linear harmonic oscillator are all proportional to the original Gaussian, okay? This is intuitive because we start with the original Gaussian and then we either multiply by some factor or take the derivative of it. So we are still left with the Gaussian as a multiplying factor. And then when we go on with the index of the eigenfunction, we find that this is multiplied by a polynomial that is called capital Hn, and this polynomial is called the Hermite polynomial, okay? So the Hermite polynomial is one of the factors of the eigenfunctions of the linear harmonic oscillator, and then there is the normalization coefficient in front of it, okay? Another thing is that it is easily found that the eigenfunctions of the linear harmonic oscillator form a real and orthonormal set of equations. So there are a complete set in which, as expected, the eigenfunctions are orthogonal to each other and normalized to 1. And finally, we go back to the original symbol. So you remember that the eigenvalue of the number operator, the quantity that we initially called ni, is actually equal to epsilon minus 1/2. Where epsilon is the eigenvalue of the normalized Hamiltonian. But in turn, epsilon is equal to the actual eigenvalue E of the energy of the harmonic oscillator divided by h bar omega. So by reversing these relations, we find eventually the eigen values of the linear harmonic oscillator, and they are indicated with E sub n because they depend on the integer n, and they are equal to n plus 1/2 times h bar omega, in which n goes from 0 to 1, etc., up in the ladder. Okay, this is a very, very famous formula. Okay, actually, you see immediately, you spot immediately the product n times h bar omega that is reminiscent of the energy of a mode of the electromagnetic field, for instance. Okay. You can see that actually there is a constant, there is 1/2 h bar omega. So even if the index is the minimum, that is n equal to 0, the linear harmonic oscillator has still an energy, and this energy is E0 equal to 1/2 h bar omega. This energy is called the 0-point energy. This is intuitive if you remember the general properties of quantum mechanics, because you remember that when the wave functions are normalizable, then the minimum value of the total energy must be strictly larger than the minimum of the potential energy. Okay? And this is the case because since the potential energy is a parabola, okay, and this parabola goes up to infinity, the linear harmonic oscillator has a potential energy that is like a box, but it is a box in which the sides, instead of being straight, are those of a parabola, okay? But the wave function is confined inside the limited region of space, okay? And it decays at infinity, at plus infinity or minus infinity, okay? So it is normalizable. And when the eigenfunctions are normalizable, you remember we have a general demonstration that tells you that the minimum total energy must be strictly larger than the minimum of the potential energy. In the parabola, the minimum is 0. It is, remember, the potential energy is 1/2 times the elastic constant times x squared. So the minimum is 0. Okay? So the minimum total energy must be strictly larger than 0, and its value in the minimum is h bar omega divided by 2. This is called the 0-point energy of the linear harmonic oscillator. We can comment. You see, the first point here was already commented because it is a comparison between the classical and the quantum situation. In the classical situation, it is possible for the particle to have a total energy equal to 0, okay? This happens if you take the classical expression of the total energy and set x equal to 0 and p equal to 0. So this is the case in the classical situation in which the particle is not moving, so the momentum is 0, and its position is in the minimum, so it is the stable situation or the equilibrium situation in the classical case of the linear harmonic oscillator. Okay. Another thing that we can do is checking what happens if we consider the normalized form of the Schrödinger equation of the linear harmonic oscillator and take the Fourier function. Let's call U the Fourier transform of W. Of course, we can calculate the Fourier transform because W decays at infinity like a Gaussian, so the transformation with respect to the transform does exist. Okay. Then you remember that when the transform of the derivative is just J times the Fourier transform itself. And the transform of the second derivative is minus eta squared times the transform. Okay. At the same time, the Fourier transform of psi squared W is like minus the second derivative with respect to eta of the transformed function. Conclusion, if you take the Fourier transform of the equation of the Schrödinger equation for the linear harmonic oscillator, you find an equation. You see it in the text. It is eta squared un minus the second derivative of u with respect to eta 2 times equal to 2 times the eigenvalue epsilon n times un. So this equation is formally identical to the original equation. So it happens that the Fourier transform of the Schrödinger equation for the linear harmonic oscillator is identical to the original equation. And also, the eigenvalue is the same because the eigenvalue is a constant, so it is not touched by the Fourier transform. So it is an eigenvalue equation in which the eigenvalue is the same as the original eigenvalue equation. Okay. But you remember that the eigenvalues of the linear harmonic oscillator not degenerate. So to each eigenvalue, to each value of energy, it corresponds one and only one eigenfunction. That means that un must be equal to wn because it is the only eigenfunction corresponding to that eigenvalue, apart from a multiplicative constant as usual because the problem is homogeneous. So that means that the solutions of the Schrödinger equation for the linear harmonic oscillator have a Fourier transform that is equal to the solution itself. So they are their own self-transforms. Now we can apply, let me check the time. We can apply this to the important case of the electromagnetic field. We do not have the time of considering in full the description of the electromagnetic field in terms of modes. So I shall only outline what happens when we manipulate the Maxwell equation. The original problem in the classical situation is the following. We take a volume of space in which we have only the electromagnetic field, no electric charges. For the analysis, it is not important what the form of this region of space is. So we take a simple form, that is the form of a box in which the sides of the box are aligned with the coordinate axis. So the sides of the box are D1, D2, and D3, and D1 starts from the origin and goes into the positive direction of the axis x1, and the same for D2 and D3. Obviously, the product D1, D2, D3 is the volume of the box in which we are considering the electromagnetic field. Then we want to calculate the total energy of the electromagnetic field inside the box. Why do we want the energy? Because when we want to operate the quantization of the electromagnetic field, and we want to write down the Schrödinger equation, remember the Schrödinger equation provides you with the eigenvalues of energy. So we must start from the classical formula for the energy of the electromagnetic field, and then we must introduce the quantization. Now, it is possible to demonstrate that the energy of the electromagnetic field inside the box is the sum of the individual energies associated to the monochromatic components of the electromagnetic field. So we call WEM the total electromagnetic energy in the box. WK sigma is the energy associated to the individual monochromatic component. It has two indices. One index is the K vector, because as usual, each mode of the electromagnetic field has a K vector. So actually, K is a triple index. You see the expression of the K vector in the line immediately after the formula. So K is a vector with three components. These three components are aligned, of course, on the axis. I2, I3 are the unit vectors of the axis. And the component of the K vector, as usual, are equal to 2 pi divided by the side of the box times an integer and I that goes from minus infinity to plus infinity. So actually, the index of the K vector is a triple infinity of integer indices, okay? The other index, that is sigma, is either 1 or 2 and corresponds to the two different independent polarizations of the electromagnetic field, okay? You may remember this term, we did not treat it, but you may have some memory of polarization from some other classes. And then you remember that each monochromatic component of the electromagnetic field has two independent polarizations, so that we need two indices, okay? This index, when we transform the analysis from the classical into the quantum description, the polarization becomes the spin of the photon, okay? The two possible values of the spin of the photons. Given that, what is the expression of the electromagnetic energy associated to each mode and to each polarization? It is given by the expression that you can see here. It is 2 times the permittivity of vacuum, epsilon 0, times the volume of the box, times the square of the angular frequency. Obviously, the angular frequency is equal to the speed of light. We are in vacuum, so it is c times the modulus of the wave vector times on time times the same function as conjugate. Okay? The form of this function is not very relevant, but you can see that W is quadratic with respect to S, because it is S times the conjugate. S is complex, okay? But of course, when we multiply S by the conjugate, we obtain something that is real, because the energy associated to each mode, of course, must be real, okay? You also remember that in order to proceed with the quantization, it is necessary that we write the energy in terms of position and momentum. So the quantity S is not suitable because does not show clearly which is position and which is momentum, okay, in this expression. But this is easily fixed because we can just introduce a change in the variables. And this change in the variables is written in the middle of the page. We simply express suitably the quantity S by imposing that S times 2 times the square root of epsilon 0 V times omega is equal to omega Q plus JP, in which omega Q is obviously the real part of the complex quantity that is on the left, and JP is, and P is the coefficient of the imaginary part, okay? Of course, we have one Q and one P because is complex. So S is actually two quantities, the real and the imaginary part. By this replacement, then the expression of the energy WKS of the individual mode becomes neat. You see it, you see the brace here. Look at the first line of the brace, okay? If you look at the first line of the brace, you have 1/2 P squared plus omega squared Q squared. But this is exactly the expression of the linear harmonic oscillator. We go back to the linear harmonic oscillator. if you take the classical expression of the linear harmonic oscillator and then you impose that the mass is equal to 1 in some units, you have p squared divided by 2. Then you have x squared divided by 2. And c becomes omega squared because the mass here is equal to 1. So p divided by plus omega squared x squared divided by 2. Then x, you call it q, because in the general language of analytical mechanics, the coordinates sometimes are called q, okay? And you have that the energy of the individual mode of the electromagnetic field associated to the wave vector k and to the polarization index sigma is identical to that of the linear harmonic oscillator. Okay. What are the other two expressions that are on the same line? The other two expressions that are on the same line are exactly the same expression as above, because if you check the extra terms, 0. QP minus PQ is 0. And again, in the third line, QP minus PQ is 0. So why did we write them down? Because when you do the replacement here of S into the original expression of the energy of the individual mode, you replace two complex numbers, okay? And then you calculate energy of the individual mode of the electromagnetic field, and these three possible expressions are those that are written here. And in principle, all of them are legitimate. But it is easily understood that if we proceed with the quantization, and the quantization is given at the bottom of the page, we proceed in the usual manner. We take each component of position, so that is each Q. We replace it with an operator, but for the component of position, the operator is the component itself, so the Q terms are left unchanged. Instead, when we proceed with the replacement of the component of momentum, P is replaced with P hat, that is the momentum operator, minus J bar, derivative with respect to Q, okay? And if we do it in the commutators, you remember the commutator of a position coordinate and with the corresponding momentum is JH bar, okay? So in this case, in the second line, we have JH bar, J and J gives you a minus. So globally, the energy, again, the Hamiltonian is real, okay? And in the last line, we have again JH bar, J with the minus J is a plus 1, Okay, so we have three possible different expressions of the Hamiltonian. This looks very unpleasant because at some point we should ask ourselves which is the correct one. Okay, but we shall see there is a way out. So let's continue on this line. And for the moment, we have to continue simply by taking all three possibilities and seeing what happens if we proceed with each of one. So in the quantization, we transform the W, that is the energy of the individual mode in the classical case, we transform it into the corresponding Hamiltonian. So the first line, we call it Hamiltonian with a zero. And of course, it is the standard Hamiltonian of the linear harmonic oscillator, in which instead of using the symbol psi for the position, we use the symbol Q. In the second line, we have the same Hamiltonian as above minus h bar omega divided by 2. So because of the minus, we call h minus. And in the third line, we have the Hamiltonian with the plus, and we call it h plus. Okay? Then we construct the three possible Schrödinger equations for each of these operators. So for the first one, we have h0 operating on some function that we call W0 equal to some eigenvalue that we call E0 times the eigenfunction. But this is already known because this is exactly the Schrödinger equation for the linear harmonic oscillator that we have just solved 10 minutes ago. Okay, so we know that the eigenvalues E0 are an integer plus 1/2 times h bar omega. You remember omega is equal to c times the modulus of the k or the wave vector, okay? And this number n must also depend on the indices of the operator. So it must depend on both the index of the wave vector and on the index sigma of the polarization. Okay. So we don't care about the eigenfunctions. We know that they are the product of the Hermite polynomials times the Gaussian, so that they are known to us. Okay. Now we go to the second equation. The second equation is such that we have again the original Hamiltonian h0 minus h bar omega divided by 2. So we bring the constant to the right. So in the second equation, we have the same operator as above, operating on W minus, equal to the eigenvalue that we call E minus plus h bar omega divided by 2 times the eigenfunction. Okay, but this is exactly the same eigenvalue equation as for the first case, okay, because we have the same operator. So this operator will provide the same set of eigenfunctions and the same set of eigenvalue as before, okay? So we must conclude that W minus must necessarily be equal to W0, okay? and the quantity in parentheses must necessarily be equal to E0. So we have found for free that E minus is equal to n plus 1/2 h bar omega, and then we have to subtract, another h bar omega half. Okay, so it is equal to nk times h bar omega. If we repeat the same analysis for the third case, we have again that W plus must be equal to W0, and that the eigenvalue with the minus is equal to E0. So the eigenvalue E plus is equal to n plus 1 h bar omega. Okay, so apparently, all these three equations are good. They provide a set of eigenfunctions that are all the same and a set of eigenvalues that are slightly different. Okay, so we now stop and we shall start it over again in 10 minutes. So it is 11:03. We shall start at 11:13. Okay, so let's start again. Let me find the page. Okay. So we were left with this problem. We have three solutions of the Schrödinger equation corresponding to the three possible Hamiltonians. These are the Schrödinger equation for the single mode of oscillation. Each equation has the same eigenfunctions, but the eigenvalues are different. So for the equation with the zero, the single eigenvalue is n plus 1/2 h bar omega. For the second equation, the single eigenvalue is E minus equal to n h bar omega. And finally, for the third equation, the eigenvalue is E plus, that is n plus 1 h bar omega. Okay, so the differences between the eigenvalues, they look small differences, but they are important because this is the expression of the energy of the single mode of oscillation. That is the mode of oscillation related to the specific wave vector and to the specific polarization. However, the original problem was to find the total energy of the electric field inside the box. That is, after finding the energy associated to the individual mode of oscillation, now we have to add up over the indices in order to find the total energy inside the box. Again, we have to do it 3 times because we have, for the moment, 3 possible expressions and we don't know which is the correct one. Okay? So let's do it. We have to sum over the 3 indices of the wave vector and over the index of the polarization. So this sum here over k sigma goes over minus infinity to plus infinity for each component of k. So it is a triple sum over k plus a sum from 1 to 2, so just two terms with respect to sigma. Now the issue is that you see immediately that the first expression and the last expression diverge. Why? Because the first expression has 1/2 h bar omega, and the last expression is a 1 times h bar omega. So h bar omega is equal to the product of c times the modulus of k. When you add over all components of k, when the indices of this sum increase, the modulus of k obviously increase, okay? Because you are adding up over all frequencies, okay? So when the frequencies become higher and higher, then the modulus of k becomes higher and higher, omega becomes higher and higher, and these terms obviously diverge. So 1/2 h bar omega diverges, and also 1 times h bar omega diverges. So we must discard expression number 1 and also expression number 3. And we must keep the expression in between. One may say, but also in this expression, h bar omega does diverge. It is true, omega does diverge when we increase the modulus of k, but the number n may be 0 from some point on. That means, using the language of quantum mechanics, that there are no photons of high energy, because the number n is 0 itself, okay? Also in the other expressions, this number n can be 0, but in the other expression we have the constant 1/2 it times h bar omega and the constant 1 times h bar omega. They do not go to 0, okay? So we can conclude that the intermediate expression is the only one that is acceptable. So we eventually have solved the riddle of the 3 different Hamiltonians, okay? And we say that these numbers n must vanish for some k on, okay? So that the total energy is finite as should be, okay? Also, we may say that since the sum over sigma goes over 2 indices only, 1 and 2, okay? And h bar omega does not depend on sigma, we can perform the sum over sigma because we have just 2 indices. We have nk1 corresponding to sigma equal to 1 plus nk2, okay? So we just call it nk, and we have a single sum. Conclusion: the energy of the electromagnetic field in the box is the sum of individual terms. Each individual term is equal to an integer number nk times h bar omega. So this is formally the demonstration of the photons. H bar omega is the individual quantum of energy associated to the angular frequency omega, that is to k, essentially, to the wave vector k. Each mode of oscillation has an energy that is equal to an integer number nk times the quantum. Nk is called the occupation number of the mode, okay? So the total energy of the electromagnetic field in vacuum is the sum of the energies of the individual modes, and the energy of each individual mode is an integer number, the energy of the photon, h bar omega. So this is the formal demonstration of the hypothesis of the existence of photons that is obtained starting from the classical expression of the electromagnetic field given by the Maxwell equation, and after many manipulations, they are reduced in the form of the linear harmonic oscillator, and then the linear harmonic oscillator is quantized, okay, and this is the end. By a very small addition, we can also find the momentum of the photon, because by a similar calculation that we shall not do, so I'm going to skip it again. We can also find an expression for the momentum of the electromagnetic field in classical terms, okay? And this expression, fortunately, is very similar to that of energy, okay? So the momentum of the electromagnetic field, here it is called with the symbol capital pi, okay? So capital pi is the total momentum of the electromagnetic field in the box, is equal to the sum, as it is intuitive, it is equal to the sum of the momenta of the individual modes of oscillation, okay? How do we define the momentum of the electromagnetic field? Let me open a parenthesis. We define the momentum of the electromagnetic field using a procedure that is similar to that used for defining the energy of the electromagnetic field. I'm sure that you remember that somewhere in some class of the field theory, somebody has explained to you the pointing theorem. Okay, the pointing theorem is a theorem of conservation of the energy. The pointing theorem is based on this consideration. If we have a region of space in which we have both particles and the electromagnetic field, and the particles interact with the electromagnetic field, they exchange energy. The conservation of the energy is described by the theorem by a theorem that is called the pointing theorem. Okay, that states that if there is a loss of energy of the electromagnetic field, this loss of energy goes either into the particles, so the particles acquire energy from the electromagnetic field, or the energy of the electromagnetic field radiates across the boundary of the box and goes away. Okay? So it is a conservation theorem. We can write down another conservation theorem for momentum. Okay? It is very much similar to what you have in analytical mechanics. The time derivative of momentum is the force. Okay, so you can set up a conservation equation for momentum, again involving the interaction of particles and the electromagnetic field. And you say if there is a loss of momentum from the electromagnetic field, then it is gained by the particles or vice versa. Okay, if there are no particles, you simply have that the momentum of the electromagnetic field is not lost against anything. Okay, but the expression is the same. So the momentum of the electromagnetic field is equal to the sum of the momenta of the individual modes, and the momenta of the individual modes have an expression that is almost identical to that of energy. You see that you have again 2 epsilon 0 V times omega times the product of S times S conjugate, and then you have a K K is, of course, the wave vector of the individual component, okay? So that K adjusts the units, and it's a vector because momentum is a vector. But you can divide and multiply this K by omega. So you obtain an expression that is in the second line. You divide by omega and you express omega as C times K. And then, of course, you multiply by omega, so omega becomes omega squared. Okay. After that, you see that the block that is inside the expression of momentum is equal to the Hamiltonian that we already met. Okay. And since we already know that the correct Hamiltonian is the one with the minus, we replace it with the Hamiltonian with the minus. Then we have K over the modulus of K, and that is simply the unit vector aligned with K. So it is a unit vector that prescribes the direction of the individual component of momentum. And then we have divided by C. But this is no surprise. We already met somewhere when we consider the relativistic expressions that for the electromagnetic field, momentum is essentially energy divided by C. Okay, so we find something that is fully consistent with that because it is again derived from the Maxwell equations. Okay. In conclusion, since the operator associated to momentum is proportional to the operator associated to energy, it follows that the eigenvalues of momentum must be the same as those for energy divided by C and multiplied by K over the modulus of K. So if we do it component by component, we have that the eigenvalues of H minus, as you remember, are n times H bar omega. Then we divide by C. And then we have the component of K. Instead of considering the vector K, we consider each individual component, Ki, okay? But then you see that in the denominator we have Ck, and Ck is omega, so omega is cancelled. And the conclusion is that the component of the momentum of the electromagnetic field along the ith direction associated to the individual oscillation mode is proportional to H bar K. And the factor is again n K sigma. So going back to the vector form, we have that the component of momentum is given by an integer multiple of H bar K, and the total momentum of the electromagnetic field in the box is the sum of these individual components. So again, we have a justification that not only the energy of the photon is equal to H bar omega, but also that the momentum of the photon is H bar K. Okay? This is important because when we want to, for instance, calculate the interaction of the photon with some particle like the electron, okay, we can consider it as a collision between two particles. And we just impose the conservation of momentum of energy that is typical of the collision of the two particles, and we can calculate the exchange of energy between, for instance, an electron and a photon when they interact. Now we skip this part. And we do the same thing with the phonons. I'm sure that you remember that at some point we have taken the crystal or a set of atoms. We have considered that the forces among these atoms are very strong, so the displacements of the atoms with respect to the equilibrium positions are small. Then we have, at that point, expanded the potential energy to second order. The first order is 0 because the expansion is around the equilibrium position of the atoms. And then we have found a quadratic form of the potential energy that, due to some properties, the quadratic form, you remember, is positive, definite, and symmetric, can be diagonalized. So we, after this process of diagonalizing the total energy of the material in classical terms, we have found the normal coordinates and the normal mode of oscillations. Okay, this is something that we have already done, and we have found the total energy of the set of atoms is given in the last line here. Okay, you remember the total energy of the atoms, this is why we are using the suffix A, is equal to the kinetic energy, Ta, that is already separated, that is always separated, plus the potential energy Va, and we have demonstrated that this energy is equal to the constant Va0, that is the value of the potential energy when all the atoms are in the equilibrium positions, plus a sum of individual terms. This sum goes over the degrees of freedom of the system. So if we have a total of capital N atoms, we have 3n degrees of freedom, and the index goes over all them. And this sum is made of individual pieces that are Hamiltonians in the classical term, H sigma, and each Hamiltonian has the form 1/2 B dot squared plus 1/2 omega squared B squared. You remember B depends on time. We are still in the classical situation. So B is the normal coordinate. This is a one-dimensional motion, okay? And omega square is the angular frequency, and as in the case of the single linear harmonic oscillator, the angular frequency is given directly by the mechanical properties of the system, that is, by the combinations of the masses of the atoms and the elastic constants, okay? So it is already there. There is no quantization for the moment. This is still a classical description. So globally, the vibrational state of the crystal or the solid can be described as a superposition of individual modes of oscillation, and each mode is described by the equation of the linear harmonic oscillation with, again, the mass is equal to 1 because there is no mass visible in the expression. The actual masses of the atoms have been embedded in the transformation of variables, okay, so they are not visible anymore. So this expression here is sufficient to proceed to the quantization of the solid. Okay, what we do is simply that we quantize each classical Hamiltonian. In this case, there is no problem of divergence and there is no problem of choice between different Hamiltonians, because in the electromagnetic case, as you remember, we were dealing with complex quantities, okay? And then we had to calculate the square modulus by multiplying each quantity by the conjugate, okay? So when you multiply, you have to select the order of the two factors in the product, okay? And when you quantize them, they do not commute, okay? So this is the reason why in the electromagnetic field you have this problem. In this case, we do not have this problem because the classical problem is already quadratic as is, okay? So there is no ambiguity in selecting the order of any factor. There are no complex quantities to be multiplied, number one. Number two, the energy is of course finite because we have a finite number of degrees of freedom, in contrast with the electromagnetic field in which we have infinite modes. Okay, here we have finite modes because we have a finite number of atoms. Okay, so there is no technical problem here. We have one Hamiltonian in the classical situation and still one Hamiltonian in the quantum situation. So now the quantization, of course, consists in transforming the kinetic energy into the kinetic operator, and this becomes a sum of quantum Hamiltonians, each associated to the individual oscillation mode. So the individual Hamiltonian depends on index sigma. Here, index sigma is the only index. It goes over the degrees of freedom, so from 1 to 3n, okay? And obviously it is equal to minus h bar squared divided by 2, second derivative with respect to b, plus 1/2 omega squared b squared, okay? Then we have to set up the corresponding Schrödinger equation. So this is the Schrödinger equation in which the total energy is written as the sum